So I'm Sebastian. I'm a developer at Jane Street. I don't know if anyone here is familiar with who Jane Street is. It's a trading company that works sort of in finance and trades around the world, and we proudly consider ourselves to be the largest industrial user of OCaml. So we write everything in OCaml, and all the systems we produce, like from trading systems all the way towards like infrastructure or systems or networking tools, everything's written in OCaml. So we have a very strong interest in functional programming. I want to talk today about Incremental, which is a library that we built in Jane Street for something that's called self-adjusting computations. So to give a quick overview of the talk, the first half of the talk I'm going to talk about sort of like what is Incremental and like what does the library give you and what features does it provide to you and how can you use them. And then the second half I want to talk a little bit, depending on how much time I have, about like what the challenges are when you implement this. Because I think it's actually a very interesting thing to think about how to implement it. And internally we've spent a lot of time implementing this, and we are now currently on our version 8 and thinking about more versions and sort of constantly coming up with like shortcomings somewhere and like how to improve things. So first of all, let's talk about what Incremental is. So this is based off an idea by Aka as a research paper called self-adjusting computations. And the idea is that you have some complex computations that depend on the inputs, and you want to run these complex computations every time your inputs change, but you don't want to run them when your inputs don't change. So the way you can sort of think about this is you build a dependency graph of where some of your leaf nodes are your inputs, and you build sort of your computations are your nodes, and finally you have outputs of like what users actually care to look at. So the idea is that the library does the minimal work necessary to update all the internal computations every time the inputs change. So in some ways you can think about this like Excel. So I don't know how many people here have used Excel or have used Excel. By the way, before I say something bad about Excel, I also want to say something good about Excel. And Excel is like in general a very powerful and very great tool, and like it has tremendous power, but it does not give you quite what Incremental gives you. So in Excel you can think about if you have a bunch of inputs and you sort of as a bunch of cells, and you like define some computations which are based off of these cells, and these are sort of your leaf nodes. So in that way it's very similar, but in Excel, like your dependency graph is static. Like you have a bunch of cells and you define a bunch of computations and you can change the inputs and change the output, and that's kind of it. In Incremental, the crucial bit is that your dependency graph itself is dynamic. So as inputs change, the structure of the graph itself might change. So a bunch of use cases, or like how we use this within Jane Street, is the first, or an original use case where this came from is for our trading systems. So often in trading systems you want to sort of build something that decides to trade or decides to send an order to a market based on some event in, like based on what it thinks is a fair value for something that you want to buy or sell, and it has to sort of keep a notion of what a fair value is. And these can be very complex and like can be derived of very many other things and very many other products. So our original use case for Incremental was building a library that sort of allows you to give inputs as of like market events. These things happen in the market, and you define computations that sort of compute some other values based on the events, and the outputs are sort of indicator of trading. This was our first use case. We've since used it in a bunch of other ways too. We've started using it for recalculating our risk models, which again are like these fairly complex and like very prone to change dependency graphs, and like updating them in real time is quite important for us. As we've thought about this more, we've also like gone into other areas. So one exciting one is the construction of user interfaces. So it turns out that this idea of defining some data and defining some computation of like what to do when this data changes, or how to go from one piece of data to its outputs, is a very useful way of designing UIs, such that you can sort of have all your code that deals with like how to like construct a UI from data in one place, and then Incremental does the right thing of like if some subset of your data now changes, it updates only the subset of the UI that you actually need to change. And as of recently, we've been thinking about how to use this for dynamic web applications, especially with the help of JS of OCaml. So JS of OCaml is a compiler that takes OCaml code and compiles JavaScript. And we've been using Incremental more, building at the final output actually sort of a web application running on JavaScript. Right. So So here's an MLI. So this is some OCaml code. I hope no one is disgusted by it. I hope it's, oh, by the way, even if you don't know OCaml, I hope it's fairly obvious what's going on. So this is basically the interface of what OCaml is. And the first thing is it's a type of tick alpha t. So this is it represents one incremental computation, where the tick alpha means something like what the actual thing is output. So you could have an incremental, it's an int t, which means like the final value you get as its incremental is an int, or a string, or a float, or any kind of other type you want to have in here. And then here's a very simple way of constructing a very boring incremental, is for just giving it the value and you get the incremental, which never changes. And then below here are like more interesting ways of actually creating variable inputs as incrementals. But the meat of the library comes from these functions. So here's a function map, which is sort of the crucial first bit, and probably very familiar to people thinking about monads or functional programming in general. So this function takes a tick alpha t, so some incremental that produces an alpha, and it takes a function from alpha to beta, and it gives you back sort of a beta incremental. So if you think about like you have some leaf node or some node in your incremental graph, map is a way of creating an edge from that graph to another node, right, where the edge is sort of the computation f, the function you've given it. Similarly, you have the function map2, which does what you would think it does. Is like it takes two of these, and it like takes a function that can take two of these and produces the final output. And so map and map2 are ways of constructing your graph and fanning out from the inputs. But crucially, map2 is actually sort of not just a logical extension of map1. It's kind of very useful because if you only have map, you can only ever fan out. So you have existing nodes and you can create new nodes of that. So you can make your tree more shallow, but you can never sort of come back and combine two nodes into one. So that's the power of map2. And there's the function bind, which is the sort of real crucial bit here, but I want to skip over it for a bit and come back to it later. So now here's the function stabilize, which, given the talk beforehand, might look a bit suspicious to you, because it is from unit to unit. So, so far we've here like quite strictly have this monadic interface, which turns out to be very useful. So if you actually take the argument from before, well, this function takes nothing and produces nothing, so it does nothing. The thing it tries to do is it stabilizes the graph, as in whenever inputs change. In our library incremental, we don't do any recomputations when inputs changes. We only do all the necessary computations once the user calls stabilize. So if you're used to Excel, you type in, so you have some dependencies, and then you change one of the input cells, and all of a sudden, everything magically sort of trickles and updates. And then incremental, we want to give the user the explicit power of when to call stabilize, which is sort of a design choice you might argue about, but for us it's important because for two reasons. The first reason is you don't want to expose inconsistent state to the user of the outputs. So if you think about like a bunch of events happen that change your inputs, and if you were to recalculate immediately, maybe but you actually only wanted to give the user the final output once all these changes have gone through, and not sort of halfway intermediate after a change that might look crazy. So like if you think about it from a trading perspective, maybe there was a very big event in the market, and if you sort of, you should really consider everything together before you sort of give an indicator to trade. So if you start like updating and then give the user halfway through, give the user an update, then you sort of might be doing a bad trade you don't actually want to do. And the second reason why you want to do this is because you want to be able to batch things. So it's often much more efficient to sort of be stable, like, I don't actually care about any updates from now, and now I do care, so please run all the updates, but you don't need to do anything in the middle, because I don't care. And finally, there's these two functions to actually sort of look in incremental and like do something with it and like get the value out of it. Does that make sense so far? Cool, so as a simple example, we can calculate the area of the rectangle with it. So excitingly, we have two variables, height and width, and we define the base area as a map2 of those two variables, where the function just sort of multiplies them, which is fairly straightforward. And then if we actually run this, we sort of first register this callback of saying, like, print it up, please, whenever it changes. And we set the variables, we call stabilize, and print it out. Hooray. And we set the variable again, and nothing is printed, and only if we sort of call stabilize again, we get the update. Does that make sense? Yes. No. That's a good question. If you don't mind, I'll come back to that. It is related. But yeah, I'll come back to it at the end. So now I want to talk about bind, the thing I skipped over, which I sort of claim is the most interesting, the most useful, but also the most complex thing to think about. So far, like everything's fairly straightforward, but what bind does is quite more complex. So if you look at the types, like it's only sort of a very subtle difference. Right? So map took a function from alpha to beta, and now bind takes a function from alpha, and it produces a beta t. So the idea here is that in map, you sort of have a static dependency, and you say your input, and then you provide a function that takes the input and produces the output. But sort of that's like a very simple one-way relation of two leaves, and the function f is the computation. While bind gives you vastly more power than that, because bind lets you say, depending on the input, here's a completely new incremental graph. So that means, like, if the input is originally this, I'll return this graph. But later, if the input changes, I return a completely new graph. And now, this is where the dependency is allowed to be dynamic, because you can actually change the graph as the input changes. So to summarize it, map and map2 sort of build the static DAGs, while bind builds the dynamic ones. And let's see how that's useful. So if you want to build a construction that represents some sort of if node, we could do that with map3 as a logical extension of map2 by just taking a condition and the two branches and merging them into, and having the function do the obvious thing of matching on the condition and executing one of the two branches. But this is somewhat inefficient because we had to create these two branches, and importantly, like our library Incremental will not know about the fact that if this condition is true, you don't actually need the else branch, or rather, if the condition is true and something changes in the else branch, you shouldn't actually propagate any updates because nothing ever changed, right? So if you use bind instead, you could say, well, the function that you give it here now gets to say, well, if the condition is true, I'm going to return my then branch, and the else branch doesn't even exist. And now, if then the condition swaps to false, now this edge has sort of gone away, which conveniently you can't see because it's right on the edge. So I promise this edge has gone away. And now the else branch is connected. So importantly, like if now we have like big computations underneath these graphs, and this one fires, Incremental will know, oh, well, you don't actually use it, so I don't have to bother recomputing anything. So one final piece of feature that we want in our API, before talking a bit about how to implement this, is cutoffs. So in our use cases, it turns out to be very useful if you have a way of cutting off computation and stop propagation. So for example, if you imagine this case of like, here's some node 5 and a node 10, and a very big dependency graph that depends on it. And now this node 5 changes ever so slightly. Well, now you change 10 changes ever so slightly, and you have to recompute the rest of the graph. So cutoffs are a way of saying, notifying Incremental that you don't want your parent to be updated if you have not changed by more than a certain percent, for example. And like in our statistical models, like that's very useful of saying like, well, if this value has changed in a non-significant way, I don't want to bother recomputing my model. Does that make sense so far? Cool. So now I want to talk a bit about the fun of implementing it. So as I said, we sort of have iterated over 8 versions, and we are by now somewhat happy with it, but I think there's still room for improvement. So if you start out with like the very first naive thing that you might want to do, you can say, sorry, one thing before that. Implementing this whole library basically boils down to having a stabilization algorithm. So once you have a way of doing stabilize, you can sort of do everything else. Everything else will sort of naturally follow this algorithm. So how do you do stabilize? Well, the first way you can do it is, well, you can divide it into 2 passes. And the first one sort of just walks from the leaf nodes, which are sort of your inputs, and you know which leaf nodes have changed. And you can sort of transitively walk the tree upwards and mark every node that you see as dirty to be recomputed. And you also keep this tiny little counter to say how many of my children need to be recomputed before I can be recomputed. And then in the second pass, you again start at the leaves, and you should recompute all the nodes that you need to. So if we have something like this, where all the computations are just adding, you change these 2 leaf nodes, and then you mark all these things as dirty, and then you first recalculate this, and crucially now you sort of have a counter because you know, well, this guy still has 1 more child to be recomputed, so you don't recalculate this guy because that would mean you recalculate twice. So you change this, and then you change this guy and this guy. So it's a very simple algorithm and it's not very hard to implement, and it somewhat works. But there are problems. So one of the very difficult things that it turns out to do when you do this library is how do you cooperate with the garbage collector? So OCaml has a garbage collector which sort of does the memory management for you, but if you don't do it right, it can also go very badly. So in this particular case, in this very naive algorithm I just described, the problem is, well, let's assume our leaves are always live, as in like some inputs point to the leaves, so the leaves will never get collected because they're like ever-changing inputs. Well, in this example, everything, like the leaves point to everything, so nothing ever gets collected. So even if you have a big graph, and then you have a bind, and you change your mind, and your graph completely looks different, everything else from the old world is still pointed to, so it never gets collected. So you just sort of accumulate garbage. So it's annoying. So the way to fix that is you do ref counting to be able to tell when a node is dead and no one looks at it, and then you can collect it. For that, you need sort of pointers both ways, both upwards to do the stabilization and downwards to update the ref counters. And you have these things called sentinels, which you can like attach with finalizers and tell, did you see sort of like, so sentinels are the thing that you give out to your user. So whenever your user wants to look at an incremental thing, it doesn't actually get the incremental node. It gets a sentinel, which is kind of act as a proxy into the incremental node. So then when the sentinel gets collected, because the garbage collector realizes no one needs it, you can attach a finalizer and clean up the rest of your graph. So that's a problem. A second problem with this algorithm is cutoffs. So I described earlier we want to have this notion of a cutoff and be able to prevent a node from updating its parent if its computation hasn't changed significantly. So that doesn't work in this algorithm at all. Because, that doesn't work in your algorithm at all because, well, we said, actually, if I can go back to the algorithm, I said that it's divided into two passes. And the first pass just marks everything as dirty, starting from the leaves without redoing the computations. Well, if you have a cutoff node, you don't actually know whether or not you should mark your parent as dirty before you do the computation, right? So you can't actually do the thing that you wanted to do, as in like, you either have to make a decision right there and then. And the only way to make a decision would be to run the computation. So this algorithm is sort of just broken for cutoffs. So what do you do to fix it? You just as optimistically assume, well, they don't propagate probably, so it's fine. So in this way, sort of, you can add an explicit cutoff node. You can say, well, probably don't propagate. It's okay. And if you then sort of in your second phase, you come to recalculate the node and you realize, oops, they did change. Well, then you just need to sort of restart your whole algorithm. And that, surprisingly, as bad as it sounds, actually works very well. So, at least in our first use case, it was the case that most of the time people use cutoff nodes. They didn't actually propagate. So this wasn't it wasn't that bad. But as we sort of had other different patterns of use, this starts to become very painful. So these versions are somewhat broken. So now begins a tale of like how to improve on this. This is an example of how you can actually manage to sort of mess up, because here you thought, optimistically you assume this guy doesn't propagate, so you can recalculate all of that. And then you come to recalculate him and realize, oops, I need to do it again. And that's sort of like the optimally bad solution. So let's have a few more ideas about how to improve on this. So the first thing you can do is you can use a topological sort. And that's probably not news to anyone who's sort of done graph algorithms before. That's like a well-understood thing, like why don't we just use it? And that kind of works. And the idea is you have like the topological sort, and you keep a heap, and you just walk the heap from smallest to largest, and that guarantees that you never update a node before you've updated its children. So that's kind of neat. A question in practice, again, is like how do you actually calculate a topological sort? And crucially, like if you have binds that change your graph constantly, do you want to be recomputing the topological sort every time? That would be quite expensive if sort of like you spend most of your time just recalculating topological sorts. So the idea is you can use a timestamp of like, normally if you ignore binds, you could use timestamps as topological sorts because something can only depend on something else if it was created afterwards. But in the presence of binds, you need to be slightly more clever by using something that's called a pseudo timestamp, which basically says, well, if my original node was 2, and I now was created, and there's another node 3, and now I'm newly created, but I want to be in the 2 of them, well, I'm just going to be 2.5. That's okay. And then a little bit of a tricky sort of algorithmic question is like, how do you actually pick numbers to do this? Like, do you pick time? And what do you do if you run out of granularity in time? Or do you pick integers? But in practice, it turns out you can like just write a data structure that sort of uses fairly good heuristics of how to initially distribute. And if you ever do run out of space and sort of run out of granularity, you can like pay for a one-time expensive operation of just redistributing all numbers. So that works in practice. So it was pretty easy to implement. Actually, one of our interns actually wrote it. But now the crucial problem is like, oh, you've done this like sort of fairly standard thing to do graph traversal, but now you have a heap, and heap's pretty slow. Like in this particular case, the heap slows you down between 1.5 and 4 times. So you've now started off with a version 1 which was sort of naive and broken in some ways, and you tried to improve it, but your performance actually kind of degraded. And there's a second problem even, which we haven't yet addressed, which is exponential garbage. So the idea here is that, I don't know how familiar you are with the OCaml runtime, but the word finalizer probably, maybe it's a badly chosen word, but it obviously, like, for me, it often indicates the fact that, like, at some point in the future, maybe the GC will run your finalizer, maybe not. But who knows when it happens. And the problem here is that the OCaml runtime is like very slow at detecting when it actually can collect something. So the finalizer actually only runs very, very late, at basically at the point when you run out of memory. So the problem is that if you have a lot of binds, your code gets very, very slow. And worse is, until the garbage collector realizes it can collect something, your garbage nodes are still going to be pointed to. So every time an input changes, those nodes are going to be recomputed. Everything's like, all the work of your computations can be done until the GC actually realizes it can collect. The idea here to solve this is that you need a way of tracking the observed world. So you need a way in the API to keep explicitly track of who is watching you, and you also need a way of explicitly saying, well, when something is not live anymore. So that if you have like the original interface, you take out these two functions, and you add this observer, which is a way of keeping exactly track of what people are looking at in incremental and what is live and what isn't. And crucially, you have the stop observing function, which is sort of a way of saying, like, stop computing this, I don't care anymore. Does that make sense so far? So now we have a version that doesn't have exponential garbage, and it's sort of usable for bind, and semantically reasonable too. You don't sort of do this silly exponential refiring, but the heap still hurts. So what do you do if a heap hurts? You eliminate the heap. And if you've paid close attention, you realize that's not quite what we did, because that was version 3, and now we're at version 6. So we tried a few other things in the middle, didn't work so well. So here we are, version 6. The idea is that you have this heap, which is slow, and you want to get rid of it. And the crucial idea is that you don't need a total order. You only need, in fact, a partial order. So if you use heights of nodes, as sort of your topological sort, then you can treat everything at the same height in the same way, because it doesn't actually matter. If two nodes are of the same height, they don't depend on each other. It doesn't matter which one you compute first. And in our use cases, we happen to have trees which are very shallow, like millions and millions of nodes, but the actual overall height of the tree is only maybe 20 or 30. So here you can get away with a very small number of integers. So instead of having this like heap, you only have an array of lists which you can sort of walk through. But there's another problem. I don't know if anyone can spot a similar problem that we had before. What do you do if you have a lot of binds and your graph changes? Do you want to recompute all the heights all the time? And basically all you ever do is recompute heights and don't do anything useful. So again, the idea is sort of a constant, or sort of a fairly common algorithmic trick of using a pseudo height, where you sort of, whenever you need to increase the height, you do, and you sort of pay the penalty, but when you can decrease it, you don't. So in this example, if you have these input nodes, and here is the edge, by the way, you sort of assign it a height 6, and later if the graph changes, oh well, I need to increase my height and everything else. So I do that work. But now, if the node goes back to this one, sorry, here you can see, I don't decrease the height anymore. So just sort of do the lazy thing I have to do, which leads to the sort of fun pathological case of if you construct a tree that sort of all it does is iterate between two, you can just keep increasing the height, and the way to fix it is to just blow up if the height gets too high. So in our case, in a configurable 128, if the height gets too high, well, you probably made a mistake. So let's just blow up. Which again sort of sounds maybe frustrating in theory, but in practice it's just not an issue. So finally, after 6 versions, we've managed to get our performance back to what it was in the beginning. And we also have now cutoffs works and the binds are efficient. So if you see the performance plotted on a graph, it's sort of like this very frustrating thing of you started out with something that you thought was your naive baseline, and all you've ever done to make it worse performance-wise. And finally, in the end, you managed to get back to the performance you wanted originally to have. And sort of as a very final last point, because I think it's a cool optimization technique, we spent a bunch more time on thinking about how to optimize it. And in the final version, we actually managed to get another 2 or 3 speed improvement out of it. And the idea here is it's somewhat technical to the way OCaml works, but it turns out that if you want to do a poor man's object-oriented programming of you have these bunch of incrementals which are heterogeneous, some of them are ints, some of them are floats, some of them are strings. You can't store them in a list altogether as you might want to do something with your graph, because the type checker won't allow you to do that. So the way to get around that normally would be to build a bunch of closures, and each incremental has a closure that lets you operate on this incremental, and that closure hides away the fact if this thing is an int incremental or a string incremental. Which is a very common pattern of basically emulating objects in functional programming. But closures are very allocation heavy, so they allocate a lot of memory and they're expensive. So it turns out there was a neat feature in the compiler that was added in the compiler fairly recently, which is called GADTs. And it's this somewhat abstract thing that came out of type theory, where it originally was maybe doubtful of or at least some original reactions were oh, really, do we need this thing in our compiler? This is some type theory work, but is it actually useful in practice? Probably just makes my code slower and the compiler take longer. But it actually turned out that this feature is extremely useful in this case because it allows you to keep a list of these heterogeneous types and hide away be able to pattern match on them and get a peek inside what type it actually is. And this was a very superficial explanation of what a GADT is, but I hope sufficient in this case. And an important lesson, I think, that goes for all software engineering is that by now we have, I think, a fairly broad use cases for this incremental library, and it turns out that applications which use incremental are very often also incremental bound, meaning the most of the time they spend running, they do actually spend within this application. So that's the reason of why you would want to go through the sometimes painful process of building an abstract or generic library. When you say oh, I want to take the shortcut to do my one own app, my need there, I'll just take the shortcuts. But building a generic app helps you to profile performance better and come up with performance you wouldn't otherwise do. So one thing, for example, which is you might think is trivial, but you would only ever do if you have a generic library is if you take a record field that contains all the information you need for one node, and you have a bunch of use cases that use this thing, you can rotate the ordering of the record fields and just try to find the one that's most efficient for the caches. And that's something we actually did. And in the end, you did get some optimization out of it. And it's a fairly stupid way of doing optimization, and you would probably never do it if you write your own app. But if you do a general purpose library, you will consider these improvements. So with that in mind, we are thinking of modern versions. There's plenty more we could do. We could do explicit memory management, as we have done in other cases, or we could think about how to collapse a node. But none of this is as trivial as it sounds on the surface. So there's plenty of more to think about. If you want to have a look or play around with Incremental, it's on GitHub. So the whole thing is open sourced, and there's a well-documented MLI, so I encourage you to have a look. And if you want to find more about the company, then here's the website. That's it.